Hello and welcome to Module 13 on training, validation, test splits, and cross-validation. So why this module? So the metrics we saw in Module 12, we talked about accuracy, precision, ROC AUC. These really are only useful if they are computed on data that the model has never seen before. Many real-world failures will not be about bad models, but they're generally about bad evaluation. And I can't emphasize this enough. A lot of amateurs in machine learning think that if they're just using or setting a state-of-the-art architecture, like a neural network, a certain kind of neural network, at all, somehow this is going to magically give them good performance. Or if they don't attend to the various kinds of problems we've been seeing throughout the course so far, and we'll continue to see, that things will just sort of work out. And that's not the case. One of the main goals of this course is to get you to be more skeptical and curious about everything that you're doing, the choices you're making in terms of modeling, but also the broader choices you're making in terms of your evaluation. And we saw this a lot in M12, but occasionally you can trick yourself by obtaining really impressive looking metrics, really high levels of accuracy, but you fail to take into account some element of computation, some element of your overall setup. You didn't scratch the surface. You weren't curious enough, and then therefore this metric that seemed to look good actually hid nothing of quality under the hood, which would mean that either you're going to go into the world and talk about your high-performing model and then just completely embarrass yourself in front of people who know better, which, of course, I'm trying to help you avoid. Or if you are able to deploy this model that looks good on its surface but actually is not a high-quality model, then you might actually have a very negative impact on the real world, right? Because EZI models are being deployed at ever-increasing rates. So if there's one thing I want you to learn is how to just think like a scientist, which fundamentally involves being curious and second guessing your results. So we're going to talk a little bit about trying to build a trustworthy evaluation pipeline. There's a lot to this, but we're going to scratch the surface on a couple of these topics in this module. A lot of this is broken down into the train, validation, and test splits. We took it for granted that we're doing this, already, but there's a little bit more of a nuance to it that we haven't really talked about in previous modules. How to do this more effectively than we've been doing it is through something called k-fold cross-validation. And as usual, we'll be talking about matching our choices to like a real decision context. So, actually, before I get there, the learning outcomes, as usual, by the end of this module, you should be able to explain and justify the roles of training, validation, and test sets, even more than you already are. You'll be able to design appropriate split strategies for a particular decision problem. You'll be able to implement train, validation, test splits, and k-fold cross-validation in Python without any leakage occurring. You'll be able to interpret cross-validation results. So we're going a bit deeper now in terms of our evaluation of metrics, and we'll use that for model selection, or we'll start using it for model selection. And you'll be able to diagnose leakage and overfitting in evaluation pipelines and propose possible fixes. So again, our goal is to ensure to the extent possible that what we say about our models is true. Right? The truth is the most important thing that we're ever going to try to pursue as a scientist or as members of society. So it's important that we have a toolkit that we know how to use, and we also have the wherewithal and the maturity to question our results. So a couple of conceptual things quickly. A training set is just used to fit the model parameters. So this can be the weights of a logistic regression. Later on in the course, these parameters will be the connections between artificial neurons in a neural network. The validation set is used for model selection and hyperparameter tuning. This is where we sort of iterate a lot. We can use this for iteration. We can change our thresholds, for example. We can change architectures entirely. We'll see later regularization strengths. So we can change all of this here. So we could evaluate the models we've obtained from a training set. We can fiddle with a couple of things, see how well we're doing on the validation set, and then return to the training set if we need to. But again, one thing we never touch until the very last moment is the test set, which is only used once, and it's used at the end to estimate the generalization performance. I can't emphasize the extent to which it's a problem that people like you and I that are putting machine learning out into the world will do an awful lot of work in training and validation. They'll obtain some results on a test set. They'll be dissatisfied that their model that they're trying to create is not as performant as someone else's model, and then they'll go back into training and validation and redesign their model and then kind of iterate at that point. If your model just doesn't work as well as someone else's model on the test set, then in some sense that is the ultimate negative result, and you need to accept it. This must not influence modeling choices, if you want to be honest. So if you go through training and validation and then you're satisfied with what you have, you go to test, suddenly things fall apart, and then you say, well, wait a second, I forgot I should have changed my threshold from 0.5 to 0.2, and then you go back to test, and then your performance is really high, then this is a form of cheating, which you do not want to do. So by convention, it should be a double quote over here, by convention, the training set is about 60 to 70% of all of the data you have, the validation about 15 to 20%, and then the remaining 15 to 20% is the test set. Obviously, these numbers have to add up, so you can't take 70% training and 20% validation and 20% test. That's not going to add up to 100% of your data set, but obviously, like, this is within reason. You're just going to partition things approximately according to those percentages. So there's multiple ways you can get to this point. You can take all of your data and you can just shuffle them around. You can permute the indices, so all of the data is just randomly shuffled, and then you can take the first 70% for training, the next 15% for validation, the next 15% for test, for example, and then that's how you can partition all of the instances of data. That works. There might be a problem with that, spoiler alert, for later in the module, but it would work at least to partition into these three different separate sets. So the overall feedback loop is we train, validate, and tweak, train, validate, tweak, train, validate, tweak, and then only when we're satisfied will we go down to the test set. So here we have our training set, we train models, we evaluate them on the validation set. Something goes wrong we're not happy about, we tune some of our methods, we retrain new models, we reevaluate them on validation, and we iterate as many times as we need to until finally we have a model that we like, we test it, and then we never tune, we report on what we obtain. So here's one of our anti-examples. So our team will train a fraud detector again, and we'll report 99.7% accuracy on the test set. This is way higher than what we saw earlier in the previous module with models that only predicted not fraud, for example, and got 95% or even 99% accuracy. Now, this looks good. Maybe this is the state-of-the-art model. But later on, we're going to discover that, well, the team repeatedly tried different model architectures and hyperparameters, and after every try, they evaluated on the same test set, the same supposedly held-out test set, and then they picked the configuration that looked best on that test set, and out of all of these different models, and then just reported that one number. So whereas you or I might iterate 100 times between training and validation, and then only once get a value on our test set, they obtained 100 different models. All of them were tested, and then whichever one got the best value, that was the one reported, right? Obviously, this is a form of cheating. It's like a class, and saying, well, like finding the student in the class who gets the highest mark and saying, this is how well our students in our class are doing. The student got 99.7%, and that's indicative of the entire class. Obviously, that's not going to be a realistic model of reality. So the problems include that the test set is essentially part of the model selection loop. We've selected a model based on how well it performs on the test set, which is what we explicitly said we're not supposed to do. And then therefore the reported performance will be optimistically biased, and it won't necessarily generalize very well, right? So maybe that one model happened to do very well on that particular test set, but on another test set, if we just happen to have shuffled the data differently and obtained a different test set, then that exact same model with the same parameters and everything else set exactly the same way will perform very poorly on this other test set that we could have obtained, right? So this is clearly something needs to be fixed. So again, in production, what happens is we might overtrust this value, right? So you can imagine taking your 99.7% performant model to a decision maker who's not a computer scientist, who doesn't know how machine learning works. They'll see this number, see that's a really high score, that's an A++ with a sticker, and they'll be very confident and they'll pat you on the back for a few moments, and you'll be proud of yourself for that one day. But then when they come back to you the next day and say your fancy model doesn't work, are you trying to trick me, or like what's going on here? This is going to be a problem for you. So why is this fragile? Why does this, choosing like all your models, just find which one works best on your tests and say this is our best model? Why is that not good? I kind of hinted at that a moment ago, but here's kind of a visualization of the same phenomenon. We got the split just randomly, right? We even if we didn't shuffle the data initially, like just taking the last 15% of all of your data and using it for testing is just one out of, a countless number of ways that you could have chosen a test set. If you were to reshuffle all of the data again and again and again and take the last 15% of that shuffle, and you get different data points in that 15%, sometimes those data points that would randomly be part of that 15% will be easy, sometimes they'll be hard, and sometimes they'll be easy and hard in different ways for different models, right? Maybe model A is really good on some subset of your data and not so good on others. Maybe another model has the completely inverse behavior. So some data points might look easy to some models and hard to others, and vice versa. You don't necessarily know that beforehand at all. Everything's just data to you. So as we're shuffling things, a easier or hard data point might move from one instance to another, from the train to test, or vice versa. And then the performance you're reporting will jump around, right? Like if all of the instances in a test set happen to luckily be really easy for model A, then model A will look really good on that test set, right? But again, if I just resampled and got another set of test data points that model A struggles with, then it'll get very bad performance. And especially if you have a very small amount of data. So if you're doing something very bespoke or very sort of like local or unique, you might not have very many labeled data points to begin with. So you have a small test set. And if you have a small amount of data, it's hard to compute like reliable statistics. So this variability that you'd get from randomly shuffling the data can be huge. So this single train or test split will give just one sort of estimate of generalization. And here I have a kind of a visualization of what I'm talking about. For a particular model's point of view, we have easy instances, which are these circles, and we have hard instances, which are these rhombuses, these sort of diamond-shaped things. So if you move this split, so I'm randomly like now bringing in I should mention also the blues are class 0 and the reds are class 1, and then the size of the marker indicates whether it's randomly sampled in the test split or not. Okay, so my first random split, this label over here, which is easy, it has label blue, right? Label 0. It's an easy negative case, and it's big, which means it's part of my test set. Down here is label 1. It's a positive case. It's a rhombus, so it's labeled as hard, and it's in my my test set also because it's big. Okay, So that's what this graph is basically. That's what it means. And then you can kind of slide down here at the bottom different random samplings of my data. So like you can see which markers are big. Those are the data points that are part of my test set. And I've actually computed down here the validation accuracy on these different splits. So in this case, the validation accuracy goes in anywhere from 0.79 to 0.83, right? A 4% difference. Sometimes a 4% difference is not huge, but like we saw in a previous module, sometimes even like a 0.5% difference can have huge consequences to the deployment of a model, right? So that difference might be on a case-by-case basis, but you can see how simply just randomly sampling different data points to be used in your test sample, or validation in this case, can have a difference, can have an effect on the performance you're reporting. So we want to be able to reuse our data in a more systematic way. Okay, in some sense, we want to have an evaluation procedure that at some point will have seen every data point for training. Right? There's reasons for this, but sometimes we want to use every data point to be used in training. We also have all this data available to us, so ideally, in an ideal world, we would like to take every data point and use it as invalidation, right? Maybe there's something really, really unique about this data point that makes it extremely hard or extremely easy for evaluation. I want it to be part of my evaluation set, my test set, at least once, so that I can say something about important about this particular data point. This is a bit of an impossibility now. How can I use every data point for training, and how can I have every data point for testing? Like we were very clear before that the training and testing sets are separate, so a data point can't be in both of these sets at the same time. So how are we going to solve this? Well, this is part of what motivates k-fold cross-validation. And it's going to be systematic and repeatable, right? So again, another really important ethical aspect of science is that you're not just taking my word for it. I can give you my data and my methods, and then you can go off and you can recreate it yourself. And if you can't, that's not good science. Okay, so all of this together motivates the idea of k-fold cross-validation. K-fold cross-validation, basically, we're going to do a split again. We're going to partition our data, but now instead of partitioning it into labels of like training and validation and testing, we're going to label them as just folds. So every partition or segment or silo of data, we'll call it a fold, and there are k of them. And more or less, they're roughly equal in size. Okay, so we'll choose what k is in a moment. For every fold, every partition of the data, we're going to hold it off. We're going to treat that fold as validation for now. We're going to combine all of the other k-minus folds together. All that together is going to be our new training set. And then we're going to more or less follow the same method we had before. We have a big training set, which consists of k-1 folds. We'll have a separate held out validation set, which we'll use for validation. We'll train on the former. We'll evaluate on the latter. And then we can get our performance like we did before. We can compute, ROC curves, precision, recall, and so on, and on the held out fold. Okay. If we do that for every single fold, we'll have k performance numbers, right? I hold out the first fold, train a model on the rest, evaluate on it. I get a precision number. I'll then take the second fold, right? I'll throw away my model. I'll train a new model on all of the other folds, evaluate it on now the second fold, and get a new measure of performance. That's the second measure of performance, which could be different than the first. And I'll just iterate in that way. Okay, so just conceptually, we shuffle the data first, split into folds, and then repeat, k times. And now we have a situation that looks kind of like this. Okay, so here at the top we have our partition of data. This row basically is just a segmentation of all of my data. You can have imagine if I have 5 million data points. I have 1 million data points in each one of these folds. Fold 1 has 1 million data points. Fold 2 has another 1 million data points, and so on. Down here at the bottom is where I do my iteration. So each of these folds that I have in red will be my validation set for one of my iterations, one of my runs, and everything else will be used for training. So My first run, I hold out fold 1, and then I'm going to combine folds 2, 3, 4, and 5 into a single training set, train a model on that, evaluate it on fold 1. This will give me my metric 1. Then I throw everything out, start from scratch. Now I hold out fold 2. I combine folds 1, 3, 4, and 5 into one big training set, train a model, and evaluate it on fold 2 and get a different metric, and so on, all the way down to the bottom. So now you can see that, well, every data point has at some point been used for training. I used, fold 5. Every data point in fold 5 was used in training in each of my first 4 runs, for example. Also, every data point was used at least once in evaluation. So every single data point in fold 1 was used in evaluation in run 1. Every data point in fold 2 was used in evaluation in run 2, and so on all the way down the line. So if there's anything weird going on, any outliers, I'm going to capture them in one of my evaluations. Here's just basically like a step-by-step pseudocode as to what I just mentioned before, so I think I don't need to talk too much about what's going on here. I'm breaking things down into indices here, so you can take a look yourself, but I'm basically describing it once again, just to hammer it home what we're doing. The new thing here is that I have k metric values, and I can compute a couple of things with them now. I don't just have one value of accuracy, I have k values of accuracy. Or I don't just have one value of precision, I have k values of precision. So now I can compute things like the average. What is the average across all of these different metrics over here? And I can also compute the standard deviation, right? How much variability essentially occurs across these different runs. Okay, I couldn't do that before. So how is that useful? Well, this will tell us something about how well things generalize. So I kind of motivated everything by talking about this kind of instance where, well, what would happen if you accidentally get a test set that just happens to be very easy for this particular model, and you get an overinflated high score for that model. It'll look really good, but then when you try to deploy it on other kinds of data, won't generalize very well. So the fact that we're doing an experiment over and over and over again with different evaluation sets means that we kind of avoided this problem, right? Maybe once we get a very high measure of accuracy, maybe on fold J we get very high performance, but on the other evaluations, which are more realistic, maybe for this model, we get results that better represent its performance, and then therefore the mean that we get over these multiple experiments is closer to what we'd want. But standard deviation also tells us something important, right? So if a standard deviation basically is kind of like a measure of a range of performance, if every fold you get has these values, these metrics that are all very close to each other, the standard deviation, or maybe variance, or another metric you're using to measure variability, will be very small, right? So regardless of what the split is, this model performs pretty consistently. If you have a very high variance across all of these folds, that can mean that, well, sometimes this model does really well, sometimes this model does very poorly. You're getting kind of a wide range of variability. And like in many things, you want to have some predictability, right? You don't want a model to be unpredictable. So high standard deviation over your folds can be indicative of a problem. So again, if the standard deviation is small, the reported mean is stable, different folds give similar results, and you can be more confident. If the standard deviation is large, then the performance is sensitive, which we don't like. So this is a bit of a kind of a digging into details over here. These fold-wise scores will enable us to do a bit of significant testing later. So because cross-validation gives one score per fold, you can compare two models on the exact same folds now. You have fold K, you can get the score. A score here can be precision, recall, accuracy on that fold for model A and for model B, and you can just compare them. You can take the difference, you can take the squared difference or the absolute difference, whatever. Like here we want to see which model is better or worse than the other. So we're not going to square, we're not going to take absolute values, we're just taking the actual difference between them. And then you can look at, on a case-by-case basis for each of these folds, what are the differences? If model A always is better than model B, these differences will always be positive, and you can see across all of your folds, so you're getting positive, so A is consistently better than B. That won't always be the case, but if A is sort of usually better than model B, then you might expect the average of this difference to be positive, which can tell you something. And if the standard deviation is also very tight, that can mean that this difference is consistent. So you're not just looking at a particular model's consistency, but you're looking at the consistency of the superiority or inferiority of this model against another model. So it's not just a random happenstance that you just happen to get lucky on this split, but it's something more meaningful. In practice, and I would love to get more into, maybe later in this course, if we have time, we'll talk more about significance testing. But there's statistics, and then there's like deep statistics on statistics. Are these differences meaningful? Is A really better than B based on all of these measurements we're having over these different folds? That can be a difficult question to answer, but one of the ways we can try to attempt to answer that question is by doing statistical tests of significance to say that this is significantly better than that. Often these tests involve multiple measurements and measures of means and standard deviations or variances. We'll go into it to tell us whether something is different or not. And we'll come back to this later, but it's one of the reasons why I like doing k-fold cross-validation, is you can compute these deep statistics and then be much more confident in your claims about your model's performance. Quick check. I would like to ask you, if you do a 5-fold cross-validation on a data set with 10,000 examples, how many models are you going to train in total? There might be more than one answer to this, but give me your rationale. For a particular data point, how many times is it going to be used in training? How many times will it be used in validation? And if we reshuffle and then build new folds, can the CV or cross-validation estimate change? So in other words, we go all the way, I'll go back to the beginning over here. We go all the way back to step 1. After we compute all of our metrics. We have K measures of performance. We have our means, we have our variances. Now we scrap absolutely everything all over again and reshuffle the data. So we technically have different data points in indices 1, 2, 3, 4. All of our folds are now slightly different than they were previously. And we'd redo the k-fold cross-validation experiment. Do you expect the estimates to change? And if so, why? And if not, why not? A little bit of math, very briefly. We talked a little bit about generalization risk and empirical risk earlier. We talked about how, for a data set like this one, which have IID samples from some unknown distribution, we talked about modeling parameters theta according to some loss function. We talked about how the true risk, or the generalization error, which is what we kind of care about, how well does this model generalize in the real world? Well, we can estimate that if we knew what P actually was. We can compute an expectation over this, over the infinite number of possible predictions we could possibly make. This would give us our true risk, but that's kind of a fictional environment, a fictional scenario. So we have our empirical risk instead, which a data set with some finite size, bar S, which we've computed several times this way. So one of the key ideas here is that training will minimize the empirical risk on a training set, and we'll obtain parameters for you in that way. But what you actually care about is the risk on some future data. Okay, so again, the whole point of training, we have spent entire modules on this when we're kind of doing gradient descent, was to minimize the empirical risk in a way that would generalize in the future. And we were kind of assuming that things in the future would resemble what we have in our training set. But like we mentioned just a moment ago, this is not going to be necessarily the case. The test sets, the data we're going to see in the future, might differ in all kinds of ways from the data we have during training. What we would want to see is the true risk on future data that we've truly never seen. So this held out test set will give us sort of like a Monte Carlo estimate for the true risk in the real world. We don't have access to that, but we can estimate that through sampling, and with k-fold cross-validation, we kind of sample over and over again different possible worlds in which we have these test sets. And by doing so, by doing multiple testing with different held out test sets, we get a more and more accurate picture of what real true risk would look like in the real world. It's still an estimate, obviously, but it's a statistical estimate, which is better than. This is a bit of a stretch now, but I'd like to include it anyway. When you have a small number of data, like a small data set, a limited data set, I mentioned how this sort of single train test split can give you very high variance, right? Like it's not necessarily a good estimate for the true risk of a model going forward. So k-fold cross-validation can reuse data efficiently. For each fold, you have training on some set, evaluate on another set. What we're essentially doing is down here this cross-validation estimate of risk. So V sub k is the size of your fold, the number of instances of data points you have in your fold. And everything from here to here is your kind of classic empirical risk for a particular set of data, x sub I. In this case, I comes from V sub k, which is your held out test set. So this gives us an estimate of performance on just the test set. That is sort of one estimate of the risk. It's the empirical risk on held out test data. It's one estimate of the true risk of your model in the real world. But we've broken things down into big K different sets. So we can just compute the average of these. What is the average empirical risk of all of these different test sets? We just sum over all of those test sets and divide by K to get our average. And then this gives us our cross-validation estimate of risk. This is a stretch. This is basically an aside. So hopefully you get this at a high level. The details might not matter so much for your exams and so on. But like, if you don't understand this, like, come talk to me. This is just an average over the risks of all of our individual validation sets. Now, how do we choose K? We kind of ignored this for a long time. Now, obviously, a large K, a K that goes all the way to the size n, like one fold, like per data point, will essentially leave only one data point out for every iteration and train on n minus one of your other data. We'll train on all of the other data. This will train on almost all of the data every time, which will give you a very low bias, but the folds will be very similar. The estimates may be highly correlated. This is going to obviously be very expensive to compute. If you have a small value of K, if K over here is 5 or 10, this can give you slightly more bias. So you'll be using less data for every training run, which is a bit of a sacrifice. But it can give you a lower variance, and it's going to be much cheaper computationally because you only have to run through kind of K instances of training a model and then evaluating it. It happens to be the case that in practice, K being 5 or 10 are just sort of the common compromises that we use. This is one of those things that I don't personally like too much. Like 5 and 10 are like nice kind of, I guess you can call them round numbers for humans. For whatever reason, but like in terms of actual data, like why 5 and not 4, or why 10 and not 11, there's so far nothing that we've seen which can tell us which of those numbers might be better to choose. And normally when we're in a situation where we have to choose a hyperparameter like this, according to intuition or according to practice or tradition, I usually view that as a failing, right? Tradition is not normally something we want to rely upon when we're doing science. So there must be another way. Unfortunately, there are other ways, which we'll talk about a bit later. A couple of examples. The first one is this synthetic fraud data set. Again, we have, here's some, I'm just producing the random data again. We have like amounts, the days since the last transaction, how old the card is, the risk score, the hour in which the transaction was made, and then is fraud is the outcome measure we're trying to predict. We've seen this earlier, but train test split is a function in sklearn that kind of very quickly does this splitting into at least train and test for us. I should have mentioned earlier that whenever you talk about train and test and you don't mention validation, normally what that means is that the validation set, that third set we talked about off the beginning, is kind of hidden within the training set. So the test set is still sacrosanct and it's still held out as being separate and only used once at the very end, at least ideally. But the training and validation is all the stuff we use in order to get the best model we can. So sometimes the validation and train set are both viewed as that first train set. So we have X and we have Y. We have all of our data X and all of our outputs Y's, and we split. We get our X's in training, X's in testing, Y's in training, and Y's in testing. We tell this function that we want 20% of the data to be held out for testing. And we also have this random state, so there's going to be some randomization to this under the hood, so we have a random state specified just so we can reproduce things in the future. If the random state is different every time, results are also going to be different every time we do evaluation, which can be hard for the scientific process. I've included this other argument on line 8. Stratify equals Y, stratify equals yes. That means stratify the data. We haven't talked about this yet, but that's part of the example coming up, is that we want the class proportions in our training set and our test set to be roughly similar to each other. Again, we'll see why this is going to be important later. This is handled under the hood for you, and if you want, I can kind of provide some extra material later that describes methods that we might want to do this, but in this case, it's handled for you, so you let sklearn help you out there. Then we have our train set, our test set, and then we have our our fraud rates. So in this example, we have 20% of the data is 300 instances, 1,200 instances for training. And then how many instances in the train set are fraud? Well, it's about 0.042. And how many instances in the test set are fraud? 0.043. Extraordinarily close. This is the result of the stratification. If you were, in fact, again, I want you to go in there and just try it yourself, copy all of this stuff to your own Jupyter notebook and rerun things and make sure you're getting what I'm getting. Set this to no, right? So don't stratify the data. And try this a few times and see whether or not the proportions of fraud in training and testing is always going to be this close across all of these runs you're going to do, or if they're going to sometimes fluctuate a little bit. And it should be the case that if you don't stratify this split, occasionally you're going to have proportions in the test set that are substantially higher or lower than they are in the training set, which would mean that, well, this test set is not really similar to the data we saw previously in training. So here I'm just producing a logistic regression model and describing its performance. So logistic regression is going to be a baseline model. You can ignore some of this other stuff for now, but I'm just basically fitting logistic regression again. I'm using the fit function. I'm using the train XY data to obtain the parameters for my logistic regression. And then I'm making predictions. So in the previous module, we got like the raw probabilities. Now we're actually making the predictions. So we're getting training predictions, and we're getting the test predictions, and then we can compute training accuracies and then test accuracies and recall. Okay, so usually how well you do on training is not as important as how well you do on testing, because obviously you have access to all of the labels during training, so it can be seen as somewhat of a cheat to say that you're getting high performance on training. But at least in this case, we actually do very slightly better on testing than we do on training, just by random luck. And at least in terms of accuracy, but just like we saw in the previous module, the recall is pretty poor, right? Only about 7.7% of all of the instances of fraud in our test set are correctly categorized as fraud. I just wanted to kind of show here that the split, nevertheless, is pretty good. So here's a visualization of the test set and the training set In terms of their proportions, obviously the test set is small, far smaller than the training set, but I'm looking at the proportions now. And you can see how similar they are. This is just a visualization of what we saw previously. So the difference we're seeing, like this bad recall over here, or this good accuracy, is not due to like kind of any unfortunate aspects of, you know, the training data being particularly easy or hard. The test data being particularly easy or hard because of its differences in sampling. The sampling seems to have been taken care of pretty well. Again, the fraud team cares more about recall than raw accuracy, so you know we don't have a model here that's really performing as well as it should. So our split, you know, we need to keep that in mind as we're moving forward. How much does recall vary across random splits? Previously we talked about taking anywhere between 15 to 20% of our data and holding that out for testing. But how much does that choice actually affect things like recall? So this graph shows just kind of a bunch of iterations of splitting the data into different sized chunks for training and testing, training a model, getting performance, getting recall, getting accuracy, and then reporting it over here. So down here, like we have all these instances where we've randomly shuffled the data and we've taken just 10% of the data for testing. We've taken the rest of the data for training, and then we do the same old train test. This data point over here basically tells us that, well, in one instance where I've taken 10% of the data for testing, I ended up getting a test recall of 50%. And down here I have a bunch of instances of test recall being 0%, which is kind of more in line with what we were looking at in the previous module. As you get into bigger and bigger test sets, what's actually happening here, funnily enough, is that I'm getting fewer and fewer instances of recall being 0. So again, every data point is an entire experiment. Over here I'm getting test recalls of about 15% or 15.8%, I guess, and so on. So all of these experiments are being run over and over again on my data. And as you move the graph from left to right, we're looking at sort of the averages. So these bars over here represent the averages. So down here, my average is my median is 0. My third quartile is only 17%. Here, my median value is about 7.7% of recall. Here, my median value is about 10.5% recall. So as you get bigger and bigger test sets, and that's the only thing I'm really changing here, I'm getting higher and higher recall values. Maybe I'm giving more and more opportunity to catch something, which is maybe what's going on here. Also, the variance in my experiments gets tighter and tighter. So when I have like very tiny test sets, and I keep on shuffling and doing experiments over and over again, sometimes by accident, by pure chance, in a small data set, I will have a split where I seem to be doing pretty well, and I'm getting 50% recall on fraud cases, okay? And this might be just the fact that I just randomly happened to sample a very tiny test set in which half of the examples were really easy for me to catch, okay? This is obviously an outlier. This is the only instance of all of my experiments when I'm getting very high recall. Normally recall is much, much lower, as we kind of might expect at this point. But then if I expand my test set and I have more and more random chances to accidentally flag something as fraud, then I'm going to eventually get true positives along those lines, which we talked about in the previous module. So therefore, any kind of instances of true positives will raise my recall, and then therefore, again, as I expand the size of the test set and expand the pool for which I can accidentally find some positives correctly accidentally, then this experiment will actually tighten up also, and I'll have more and more opportunities to randomly find these true positive instances of fraud, and then therefore the variance will also change. I think this is a very interesting graph, right? So like it shows several things, like I mentioned, but it generally shows that the performance you're getting from doing these experiments can change drastically by simply just changing the amount of data you're using for the train test split. And it also tell you something about how consistent you will be in terms of these metrics. Okay. This again, I want to emphasize this again because I think it's important. A lot of what we're talking about in machine learning is going to be about the models, and it's going to be about how this parameter relates to that parameter, and how we go about actually adjusting the parameters using things like gradient descent. That is super interesting and obviously very important to machine learning because that's the learning part of it. But big picture, machine learning is being used in experimental processes. We're reporting results to people, to ourselves and to others. And what this graph shows us is that regardless of how carefully you've chosen the architecture you're going to use and how smart you were in terms of setting up your loss functions, something as simple as changing the proportion of your test set can give you drastically different results. And we need to be aware of that. We need to be constantly curious. Otherwise, these kinds of issues can fall through the cracks. I want to talk again about data leakage. So data leakage is essentially, again, the information from outside the training data for the model that will leak into the model fitting process. We saw this in a previous module on the rulers that were put next to lesions, skin lesions that were probably cancerous or malignant anyway. These were information in the world where an expert would give information to through the model fitting process that kind of shouldn't be there. This can happen a few ways. So if you pre-process on the full data set before splitting, you're using information about what's eventually going to be in the test set to help you clean up your training set. That's a no-no. Using test labels during feature engineering. We'll talk about feature engineering later, but if you're trying to figure out which features are the best in order to train a model, but you're using information from your test set to do that, that's also a form of data leakage. Even if eventually when the training only happens on instances in the training set, well, I've already chosen features based on information from testing. That's information leaking from test into train. Temporal leakage is kind of the same thing, using information from the future to predict things in the past. So like if you have information about a patient being discharged from a hospital in the future, and you're using that to predict when they arrive at the hospital, whether or not they're going to be admitted or not, that's obviously cheating. And then group leakage, I'll talk about it more in a moment, but if there's one user or a patient who has multiple data points, like maybe a patient keeps on coming back to the hospital, they're generating lots of data points in that hospital. Some of that data might be randomly shuffled in training, some of it might be randomly shuffled in test. That's a bit of what we call group leakage. We have a group of data, and there's some information behind the scenes that's occurring both in training and testing, and we'll talk about this in a moment. Again, the consequences are when we're leaking information, we're kind of cheating in some way. It's like having the answers to a test before you get the test. This gives you over-optimistic, like overly inflated metrics that are not going to replicate well, and replication is so important. Again, you want to avoid being embarrassed in the future, so you want to make sure that what you say about your model is as accurate as possible, and so you don't want to be overly optimistic and say, hey, I'm so smart because my model is 99.7% accurate, when in fact it's not. Misleading model comparisons, saying that your model is better than someone else's model, is basically very similar, but it's a somewhat different problem, but it's a problem you want to avoid. And again, like all of this is that if you're going to be deploying your models in high stakes settings, or even in non-high stakes settings, to be honest, then you can harm stakeholders. In this case, well, everyone from patients to doctors to loved ones and so on. So a little bit of an example. So scaling before splitting. So here I'm using a scaler. I'm using something called a standard scaler, which basically just scales all of the data. So like imagine you have data that is on a like the dimension X, and it can be extremely large. It fluctuates from extremely big negative numbers to all the way to very big positive numbers. And then you have another input variable which fluctuates over a very small little range, right? Like someone's step count per day, for example, fluctuates over a relatively big range, from like 1,000 steps per day to maybe 20,000 steps per day. But someone's age will fluctuate over, if they're using an app, like a wellness app, it might fluctuate over the range of like the high teens to like the low 80s if you're lucky, which is a smaller range. So if we're trying to scale all of the data so that it falls on a more or less similar range, that's some kind of pre-processing we tend to do with data. But here what I'm doing is I'm taking all of my data X and I'm scaling it right away. And then I'm using my X scaled data, and then I am splitting it into training and testing and so on, okay? And then you go ahead and do your classification experiments. This is bad because now the rows that eventually will be part of my test set informed the scaler, and it told the scaler this is how you want to normalize those dimensions X, right? Like if you're computing like an average or a min-max range and you're using information in the test set, then the information in the test set will inform the statistics that will tell you how to scale things, and that will give you a different value of scaling than it would if you did only use the training data. So generally it seems so small, like where all I'm doing is scaling the data, like who cares? But this is still a form of data leakage that you need to avoid in order to be an honest and upstanding